Okay, welcome. Apologize that I was not here yesterday, especially to the speakers. Really sorry, but today I'm very happy to welcome here in Pisa, and it's a great pleasure for me to introduce Daisuke Kishimoto from Kyushu University, and he's going to talk about Tverberg's theorem for cell complexes. Thank you.
Thank you. Uh, Thank you for the introduction, and I'm happy to be here. All right, so let me explain why I chose this topic for this conference. The name of this conference is Kata. So the first C is combinatorics, right? And Tverberg's theorem is result in combinatorics. So I have this one, okay? And I'm gonna generalize a result in combinatorics or bring this result in combinatorics into algebraic topology. So we have cell complexes here. So I have AT here, right? So the problem is the last one. Actually, I have an application. I have several applications of this result to pure math. So maybe this is question. All right. So, but I have 3 out of 4. So this is nice for this conference, I think. All right. So, all right. So let's start with kind of child play. All right. So let's start with a very old result of Birch in 59. Birch he's the guy in who conjectured that in a very famous conjecture in number theory, like Birch-Swinnerton-Dyer conjecture. Okay, so I think he got this result when he was in graduate school or undergrad, maybe. All right, so suppose you have 3 endpoints in the plane, any point, right? Then they determine n triangles having a point in common. Right. So more precisely, if you have 3 endpoints in the plane, you can partition these 3 endpoints into n subsets consisting of 3 points, pairwise disjoint n subsets of 3 points, such that their convex halves have a point in common. Right. So this is very catchy, and I like this. So let's try this theorem for small n. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. You want more 3? Okay. All right. So let's see. Okay, here. 1 triangle here. And we can take 1 more triangle here. And then we can take 1 more triangle here. So there is a non-trivial intersection of these 3 triangles, right? So that's the meaning of this theorem. All right, so but let's look at this intersection. Actually, you don't have this triangle, all of this triangle. Only all you need is this edge, actually, because the intersection includes this edge. And also, you don't need whole of this triangle. You only need this edge. So we can improve this theorem a little bit. like this. This is also done by Birch in the same paper. All right. Any three n minus 2 points in the plane determine and okay, pairwise disjoint and subsets. Okay, whose convex has have a point in common. Oops. All right, so this is the main result of the paper of Birch, published in 59. And of course, what you consider next is whether we can generalize this result in higher dimensional Euclidean space. Right. So that's his conjecture. Right. And after 7 years, the conjecture was posed. Tverberg proved that the conjecture of Birch is true. Yeah. No, there are many. Yes, that's also an interesting point. I'll count the right partitions. That's actually very hard. Thank you. Okay, so to solve that kind of problem, we need a kind of mapping space, a kind of discretized mapping space. All right, so and this is the Tverberg's theorem, 66. All right, so actually this was the conjecture of Birch, and Tverberg solved it. Any d plus 1 times r, or mosquito, minus 1 plus 1 points in RD can be partitions into R pairwise disjoint R subsets. Whose convex halves have a point in common. And actually this d plus 1 times r minus 1 plus 1 is the best possible number for this theorem. All right. So I want to generalize, I want to bring this theorem into algebraic topology. So to this end, I translate this theorem in terms of the an affine map from a simplex into RD, right? So this is equivalent to the following statement. Any affine map F from delta d plus from d plus 1 times r minus 1 simplex into RD, right? Determines pairwise R faces of this simplex whose image under F have a point in common. All right. So of course the d plus 1 times r minus 1 plus 1 points in RD, there is a one-to-one correspondence between these points and an affine map. Okay. And sorry. Where is disjoint? Sorry. Thank you. All right. So the configuration of these points correspond to the affine map F. And pairwise disjoint faces correspond to this partition. And the convex house correspond to the images of under F of the face. Okay? So these statements are equivalent. All right. So okay. So for the first step, I pose a question. I ask a question whether this is true if we replace this affine map with a continuous map. Okay. So in Verti's theorem, this means that we are not considering a triangle. Instead, we are considering a distorted triangle. Right? All right. And this question already has an answer, which was first proved by Pilani and his collaborators, and later Zaidin and Volovikov generalized this result. All right, so to state the answer, I set some terminology for it. All right, so let's recall that CW complex is regular if its attaching maps are homeomorphisms into. Okay. The point here is that a regular CW complex is naturally homeomorphic to the realization of the phase poset of it. All right. So it's a CW complex which can be treated as a simplicial complex. Right. All right. So and we call every closed phase closed cell of a regular CW complex by a phase. Okay. Okay. All right. All right. And now we define an almost embedding. Right. So here's the definition. Now let X be a regular CW complex. Right. And we say that a map, a continuous map, F from X into some space Y is an R almost R embedding. If for any pairwise disjoint faces, say sigma 1 to sigma R, its image under F do not have a point in common. They do not intersect. All right. So this is so you can think of this almost R embedding is a discretization of non-R equal embedding of a space, right? And of course, an embedding is an almost two embedding, but the converse is not true. Okay, and we are interested in the non-existence of and almost R embeddings. So it's stronger than the non-existence of non-R equal embeddings. But in some cases, almost two embeddings and embeddings are the same, actually. The existence are the same. All right, so having this defined, let's state the topological version of the Tverberg's theorem. All right, this is defined first by Pilani and his collaborators when in 1991 and some others. Okay, all right. All right, we use this description expression of the theorem. All right, so any continuous map F determines pairwise disjoint R faces whose images under F have a point in common. Okay. All right, but we have another. We need additional condition on R whenever R is a prime power. Right. If R is not a prime power, this does not hold, actually. So as you can see from the proof of this theorem, this condition is seems quite technical. Actually, it's used to apply Borel's localization theorem. But this is really essential. It's related to the action of the symmetric groups. All right. So anyway, we have this topological version. And in this talk, I pose a further question. All right, now we are considering continuous map. So why are we hung upon a simplex? We don't need a simplex, actually. I mean, is there other simplicial CW complexes for which the topological Tverberg's theorem holds? That's my question. Okay. And actually, this question has a long history. The first special case was asked by Tverberg himself. He asked whether this holds for convex polytopes instead of a simplex. This is a special convex polytope. But this question is actually, this question doesn't make sense because, you know, you don't need a continuous map F from the whole of simplex. You only you need is the continuous map from the boundary of a simplex. So to generalize this to a convex polytope, we only need a continuous map from the boundary of a convex polytope. And the boundary of a convex polytope is always a refinement of the boundary of a simplex. So the convex polytope case follows immediately from this topological version. And later, there are several examples of simplicial complexes for which this theorem holds. For example, Blagojevic, Haas and Tigler constructed a family of infinitely many matroids for which this topological version holds. But the point here is that all the examples are constructed purely combinatorially. That's fine, but I've been doing algebraic topology, so I'm not good at combinatorics actually. So I want to bring this into algebraic topology. Right. So what I want here is the answer to this question. Is there a topological condition on a regular CW complex? By which this topological version holds. Okay. Okay, this is my question. Yeah. Yeah. Right. So for the topological version, this is the statement of the theorem because right. So the one here is the original Tverberg's theorem, and if we write affine here, that's the equivalent statement. Yeah. Uh, 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 yeah, left-hand side, and it's equivalent to the affine version of this. All right. All right, and this is a very general question. And also I have a more specific question on topological generalization. Right, so as I said, this theorem is actually for a continuous map from the boundary of a simplex. Okay, so the boundary of a simplex of dimension d plus 1 times r minus 1 is a special simplicial sphere of dimension d plus 1 times r minus 1 minus 1. So the more specific question is that we can generalize this theorem to a continuous map from a simplicial sphere of dimension d plus 1 times r minus 1 minus 1. Right. And of course, if a simplicial sphere is PL, this is almost trivial. The answer is almost trivially true. But there are a lot of non-PL spheres, so the answer is not trivial. Right. All right. So to state okay, I will give an answer to this question by introducing a class of nice regular CW complexes, including a simplicial sphere, including all simplicial spheres. Right, to introduce this CW complex, let's set some notation. Right, let X be a regular CW complex. All right, okay, so and we take R faces of X. Right, so for these faces, we define the subcomplex X of sigma 1 to sigma R, which is a subcomplex of X, to be the subcomplex of X. Okay, so consisting of faces disjoint from these faces sigma 1 to sigma r. Right. So it's actually the deletion of open stars of sigma 1 to sigma r from X. Okay. All right. And let's recall that space Y is n acyclic if the first one is it has an isomorphic it has a homology isomorphic to a point up to dimension n when n is non-negative and y is non-empty or n is -1 for the -1 case. Okay. All right. Now we can state the main theorem of this talk. Oh, no, sorry. Now we can introduce a new class of CW complex. Actually, the definition is somewhat complicated, but you can easily check each condition. So you can get many examples of this CW complexes. All right. All right. Okay. A regular CW complex. Let's take a regular CW complex X. Okay. And then we say that it is R complementary and acyclic if for any k between 0 and R and any pairwise disjoint k faces of X, say sigma 1 to sigma k of X, the subcomplex X of sigma 1 to sigma k is, this is rather complicated, n minus 1 minus in minus dimension sigma 1 minus dimension sigma r acyclic. Okay. All right. All right. So let's see the simplest example, the simplex. If you take a simplex, n plus 1 simplex, and take k pairwise disjoint disjoint faces, okay, sigma 1 to sigma k. Sorry, this is k. Now, okay, let's consider the case when X is a simplex, n plus 1 simplex. Then if it's not empty, it's a simplex, lower dimensional simplex, so it's contracted. So we can say that n plus 1 simplex is k complementary n minus k acyclic for any k between 0 and n plus 1. Right. All right. I'll see some more example later. All right. So now I can state the main theorem. All right. Now let X be an R minus 1 complementary d times r minus 1 acyclic regular CW complex. Then, if R is a prime power, X does not have almost R embedding. Into R to RD, right? So if this means that if you take R pairwise disjoint faces from X, then its image by a continuous map into RD must have a point in common. All right, this is our main theorem. And from the observation on the simplex, this recovers the classical topological version of Tverberg's theorem. But the point here is that, is there such a regular CW complex other than a simplex? All right, so the next propositions shows that there are a lot of interesting regular CW complex satisfying this condition. All right. Right, any simplicial n sphere is k complementary n minus k acyclic for any k between 1 and n. Right. Right, the proof is not is easy actually. All right, so just take k this pairwise disjoint faces from this simplicial sphere. Then you can evaluate its homology by using the Nerve theorem. Then you can apply the Alexander duality to get this result. That's not very hard. Right. The point here is that any simplicial sphere, not polytopo or PL sphere, any simplicial sphere. Right now, I can apply this theorem as proposition to our main theorem to get a result on simplicial spheres. All right, here's the corollary. If R is a prime power, then any simplicial d plus 1 times r minus 1 sphere does not have almost R embedding. All right. All right, so the main theorem is an answer to the general question, the topological condition for the Tverberg's theorem. And this corollary is a complete answer to the specific question on the simplicial spheres. Okay. All right. Actually, we can get more simply show complexes satisfying these conditions, but it's rather complicated, so I'll skip here. All right. Any questions so far? Right. Okay. Okay, let me explain the proof of the main theorem very briefly. We use configuration space for the proof, but not the usual one, the discretized configuration space. All right. So the ordered configuration space appeared yesterday, the last talk, maybe. Right, it's something like this. The ordered configuration of endpoints in a space X is like this. All right. Of course, this is used to study the existence of or the non-existence of an embedding. All right. So, but here we are considering a discretized version of the non-k equal, non-r equal embeddings. So we want to discretize this configuration space. Okay, that's the discretized configuration space. All right. Let X be a regular CW complex. Then we define the discretized configuration space of X. Which we denote by conf and X. Maybe this is not the right, a good notation for discretized configuration space. I think in the paper I used some calligraphy or something like that, but I can't write it here. Okay, so it's the subcomplex of the product of n copies of X consisting of faces sigma 1 times to sigma r, n, such that sigma 1 to sigma n are pairwise disjoint. Okay, so by definition, the ordered configuration space is an ordered configuration of distinct points in a space X. But here, the discretized configuration space, conf n X, is the space of configurations of n distinct faces, right? So that's why we call this space the discretized configuration space, right? Okay, right. Of course, the symmetric group sigma n acts on conf n X by permitting the coordinates. The action is free, actually. All right. And we also consider a space like this, R to D, n minus delta. Delta is the diagonal set. So it's a diagonal set in this product of nth product of RD. Then sigma n also acts on this by permitting coordinates, right? And the point here is that if there is an almost R embedding, F from X to RD, X is of course a regular CW complex, then we get a map conf n x into r d to the n minus delta, which sends x1 to xn to fx1 to fxn. Okay, this is well defined because the f is an almost R embedding. No, points. If you define an image of a point, you can get the image of faces. All right. Okay. And the point here is that this map is sigma n equivalent. There is a map. Okay. Okay. There is a map. There is a sigma n map from conf n x to r to the d to the n minus delta. All right. So now we want to prove that X has no almost R embedding. So we want to prove that there is no such a sigma n map, or some there is no G map for some subgroup G of sigma n, right? And to do so, there is a standard theorem. That's Bousfield theorem, right? Or maybe you can say it LS category or something. Right, here I will use the following version of the Bousfield theorem. Right, actually I don't know who first proved this, but it appears at least in the paper of Bolovikov. But actually it's not a proof. This is an easy consequence of the Borel localization theorem. All right, now let G be Z mod P to the K. All right, so elementary abelian P group of rank K. Of course, P is a prime. And let's consider G spaces. And both X and Y, and suppose both X and Y have no fixed points. Right? Then we can say that if there is a G map from X to Y, and Y has the homotopy type of the n sphere. Actually, we only need to say that Y has the same homology as the n sphere, but right. But then we can say that X is not an acyclic. Right. So when P is 2 and K is 1, and X and Y are spheres, this is the classical Bousfield theorem. And as I said, this follows immediately from the Borel localization theorem. Of course, to apply it, we need the group to be the elementary abelian P group. That's the point. All right. Now we want to apply this theorem to prove the non-existence of a G map from conf n x into Rn, Rdn minus delta. To apply this Bousfield theorem, we have to check that these have no fixed points. All right, And to do so, we assume that n is p to the k, and g is z p to the k, right? Of course, G acts on confen X freely, so it has no fixed points. Of course, all right, sorry. Okay, we regard G as a subgroup of sigma n by the action of G onto G itself, okay? So it's a permutation of G to the K, so it's a permutation of n elements, so we can regard this group G as a subgroup of sigma n, right? Then G acts on confen X and it's free, right? And also G acts on G itself transitively because it's group. So G acts on this space without fixed points, okay? All right, so the first condition is satisfied. The second one is that Y is homotopy equivalent to a sphere. And that's easy. This is homotopy equivalent to a sphere. Actually, this is homotopy equivalent to S of sphere of dimension D times n minus 1 minus, minus 1. Okay, that's very easy. So now we can apply this Bousfield theorem to our case, this case. All right. Right? So what is left is to compute the acyclicity of confen X, right? That's the hardest point, actually. Of course, we know it's cell structure because we know the cell structure of X, but it's hopeless, or almost it's hopeless to compute the homology of confen X from the cell structure of X. So what we do is to consider an analogy of the Fadell-Neuwirth fibration for the ordered configuration space. Okay. All right, let's recall what the Fadell-Neuwirth fibration is. So suppose you have a connected manifold, topological manifold. Then the nth projection from Fnx onto X is a fibration. It's actually a fiber bundle with fiber Fn minus 1, X minus some point X0. Any point will do. Right. This is a very famous fibration. And from this fibration, we can compute the homology of Fnx by induction and in principle. But we are now considering the discretized version. So we don't have such a nice decomposition of configuration space. But we still have a homotopy decomposition of the discretized configuration space, right? I mean, we can describe the discretized configuration space as a homotopy colimit of some functor, right? So it's actually motivated by this Fadell-Neuwirth fibration because homotopy colimit of a functor of a category C has a natural map onto the classifying space of the category C. All right. So if we have, so that means that if we have a nice fiberwise structure, we have a chance to describe the space as a homotopy colimit. Actually, this is a very old idea. Maybe it's first observed by Grothendieck. All right. Let's define a functor. right? Okay, X is a regular CW complex as before, and we define a functor Fn from Px into the category of topological spaces. Here, Px denotes the phase posets of X. So its realization is naturally homeomorphic to X itself. All right, we define this functor by the following data. F and sigma is a face of X, the closed cell, is conf n minus 1 X of sigma. Right. X of sigma is X deleted the open star of sigma. So this is something like this, okay? Very similar. All right, and if we have an inclusion of faces from tau to sigma, we define a map Fn sigma to Fn tau by the following inclusions. Fn sigma is nothing but X of sigma, and Fn tau is conf n minus 1 of X of tau. And tau is smaller than sigma. So X sigma is a subcomplex of X tau. Then there is an inclusion here, right? This map is an inclusion. Now we define the functor Fn by these two data. All right. Right. This is quite similar to the structure of the Faraday-Neuwirth fibration, but we are allowing a lot of singular fibers. And there is a very nice homeomorphism between conf and X and the homotopy colimit of Fn. Right. Actually, this is actually the main theorem in this book. Right. So now we have this homotopy decomposition of the configuration space. We can compute we can compute the homology of this configuration space by the Bousfield conspectral sequence of this homotopy colimit. Right. All right. Now let's compute the homology of this configuration space under the assumption that X is R minus 1 complementary and acyclics. Okay. Suppose X is R minus 1 complementary and acyclic. And we want to say that we want to show that in this case, conf Rx is n acyclic. Okay. All right. Now we compute the homology of conf Rx by induction on R. And when R is 1, this is trivial because conf 1x is x. And by definition, it's n acyclic. Right? So the base case is trivial. And we assume the R minus 1 case. All right. Then now we compute the Bousfield conspectral sequence. Its E1 term is isomorphic to the direct sum of the homology of F R minus 1 sigma. Here, sigma ranges over all simplices, all faces of dimension P. Right. And this is by definition conf R minus 2 x of sigma. And x by the induction hypothesis, x of sigma is R minus 2 complementary n minus dimension sigma acyclic. Actually, we define the complementary acyclicity to guarantee this property. All right. From this, we can get the following figure of the E1 term of the Bousfield conspectual sequence when the total degree is at most n. It's actually 0 except for the 0 line. And the 0 line is actually the chain complex of the realization of Px, right? Up to dimension n, okay? And as I said, x, because x is regular, the realization of Px is homomorphic to x. So it's n acyclic. So this is 0 up to dimension n. Right. So that means that conf Rx is n acyclic. Okay, that completes the proof of the main theorem. All right, for the last 1 minute, I will mention about possible or applications of this result. I applied this result to generalize the classical Van Kampen-Flores theorem. It's also on the non-existence of almost embedding. And also I think I gave this talk last week actually, and Luigi also asked about another possible application of this. And at that time I couldn't recall the possible application, but I had some indirect application of this idea. I used this idea of the homotopy decomposition to get the similar homotopy decomposition of the space of committing elements in a Lie group. Right. Actually, the functor is not the functor for the space of committing elements is not as easy as this case, but we can do it. And by using this homotopy decomposition, we can also compute the Bousfield conspectual sequence. And what I did is that to compute the torsion in the homology of the space of committing elements. And I actually, for example, I proved that the space of committing elements in SUN has P torsion if and only if P is at most n. So it has a lot of torsion. All right. And actually, there are other possible applications, but I have no time. I'll stop here. Thank you very much.
Many thanks for the nice talk. Questions?
Yeah.
So your main theorems were negative results. They were saying that the non-existence of
Non-existence?
It said that they were non-existent.
Yeah.
Do you have positive results as well in any cases?
Positive result depends on the space. I mean, CW complex.
Sure.
Yeah.
But other than the simplex case, for example.
Other simplex case, that's the best possible. So if the simplex has lower dimension, it always has almost embedding.
Right.
I have also a question. You mentioned, you had to use this primeness condition to have the symmetric group action doing everything fine. You have counterexamples in the other cases, or?
Yes. No, so you mean non-prime power case?
Yeah.
Yes, yes. There's a counterexample. And actually, many people are trying to generalize the topological version of Tverberg's theorem for non-prime power case. And actually, I think every 3 years, a paper is uploaded in archive, but there is no right one at the moment.
Further questions? Well, if not, let's thank the speaker again. All right. So let's go for the second talk today. Speaker is a great honor to introduce you, Brian Levi from the University of Aberdeen, and he's going to talk about realisability of fusion system by discrete groups. Thank you.
Thank you very much. Thanks for the introduction and the invitation. And so there is a mystery that I don't know how to solve. Maybe the organizers can help. So it turns out from the beginning, when I agreed to come, I'm in a special session. I'm not sure what's special about the session. You could maybe explain it to me. My wife claims it's because I'm the oldest guy in the room. I think that's true, but I don't think that's the reason, because in the last two katas, it was Irakli, and he's half my age, roughly, more or less. Oh, really? Okay, I thought I checked it in the online just before. Okay, I believe you. I can figure it out. I see. Okay. I should need an explanation at some point. Anyhow, let's actually do something more interesting than that mystery. So this unlike the previous talk by Daisuke, I only fit in the A and the T. So that's the two things in the middle, the algebraic topology. I don't know of any applications. And well, if you consider groups as being discrete groups as being combinatorial objects, which you could, then I also fit with the combinatorics. But there's no applications really, and that I'm aware of beyond algebraic topology. I need to tell you though what is fusion systems and where all this comes from. So this is a project which started, give or take, 25 years ago in collaboration with myself and Carlos Broto and Bob Oliver. And Bob Oliver. And so what's the idea? The idea was the following. We were interested. Ooh, this really is heavy. We were interested in spaces of the following form. If you look at the group G, right? You take its classifying space, and then you apply to it the mechanism known as p-completion, which is basically a functor from spaces to spaces, which isolates the properties of the space that are visible through mod p homology or cohomology. So p-completion. Okay. Once you do that, of course, BG is a k-pi1, G1, sorry. So it has only one homotopy group in dimension 1, which is G itself. Once you do that, most of the time, it will become a space very rich in structure, right? It has, for instance, it will have, in general, homotopy groups in arbitrarily high dimensions. Okay, so it's an infinite dimensional space if G is finite. And it has various other very interesting homotopy properties. And there was a lot of work was done back in the late 80s and early 90s, not necessarily with finite groups, but for compact Lie groups, for instance, by Dwyer Wilkerson and some other people, to try and isolate the p-local homotopy theory of classifying spaces of things like compact Lie groups, finite groups in particular. The finite groups was my own slant, but there was a lot of work also done for compact Lie groups. I'm going to talk about this in a moment. So the general question was, what can be said? So what makes these spaces special? And some things were known. Some things were known already. In other words, for instance, you knew that if you have two spaces like BG completed at P and that are equivalent, so BG completed at P is equivalent to BH completed at P, they will have the same CeLO P subgroup. That was known for ages, but I think, I'm not sure who proved that, but anyway. Nishida, maybe? I don't remember. Japanese mathematician, that's I'm pretty sure of. Not Nishida, I'm not sure who. Anyway, that was known. Other things that were kind of known or conjectured were that if you're looking at the CeLO P subgroup of the group G, and you look at the subgroups of that CeLO P subgroup and the way in which they conjugate to each other, that has a lot to do with this homotopy type. So let me make a definition now. So if S is a CeLO P subgroup of G, I want to define the fusion system of G with respect to S. It doesn't really matter which one you choose because they are conjugate in G. And this is a category. It's a category with objects are the P subgroups of S, of the subgroups of S, all of them. And the morphisms from P to Q are, I'm going to write it like this, it's hom G from P to Q, which means all the maps from all the homomorphisms from P to Q, which are induced by conjugation in G. Okay? So in other words, if G, PG inverse is a subgroup of Q, then you have a conjugation homomorphism from P to Q, and that's going to be a homomorphism in this category, okay? And so it was proven by Martino and Pridi. It's Martino and Pridi that it's roughly 1992, that if BG completed at P is equivalent to BH completed at P, not only they have the same CeLO, they have isomorphic fusion systems. Then FSG is isomorphic to FSH. I already told you that they have the same CeLO or isomorphic CeLO P subgroups, so you can find an isomorphism in the categories, and in fact they proved a little more. This isomorphism preserves the conjugation structure. Okay, so it's a stronger statement than just an abstract isomorphism of categories, but rather they call it isotypical. They actually claimed the theorem both ways. It turns out that their proof was wrong going this way. So if you have isomorphism of the category, even the strong isomorphism, they claim that then the spaces are homotopy equivalent, which turned up to be, well, their proof turned out to be wrong, okay? The statement is true, but the proof was wrong. So this was the motivation for creating this new concept I'm going to talk about, actually. So I just told you about fusion systems, but what Carlos, Bob, and I wanted to do is basically to fix this direction. So we came up with another concept which is related. Mathematicians need to be strong in Italy. Okay, so we came up with what we call a linking system. So what happens? Let me just tell you what happens for these fusion systems. What happens in the fusion systems is that this set, hom GPQ, you can think about this as follows. Hom GPQ is nothing but, you take the set of all elements in G which conjugates P to Q. This is called transporter. So NGPQ, all the elements of G that conjugate P to Q, okay, into Q. And then, two such elements can give you the same homomorphism, and the difference will be in the centralizer of P. So you divide out the centralizer in G of P, okay? This is exactly this set. What's the problem? You want to get the mod P homotopy type of the classifying space. What happens with classifying space when you P complete it? That's what you want. So you might not like to divide out any p torsion, right? The centralizer of a p subgroup will typically contain its center. Well, not typically, it will always contain its center. The center is a p subgroup, okay? And you are dividing it out. So you're destroying information when you do this. So the idea was, let's put it back in. Let's take a family of subgroups which behaves nicely. This is called the p-centrics. Turns out by some deep theorems in representation theory, it turns out that the p-centric subgroups actually control everything. They control all the conjugation patterns between all the p subgroups. What are they? They are those groups such that if you look at CGP, CGP is isomorphic to the center of P, cross, canonically isomorphic, cross with CG prime P, where CG prime P is order prime to P. Okay? So instead of looking at the dividing the transporter by CGP, divide by CG prime P, thus leaving the center in. Okay? So you define the linking system, LS centric of G, to be the category with the objects, the p-centrics, and the morphisms from P to Q is the set NGPQ divided by CG prime P. Okay? And that turns out to be the right thing to do in the sense that if you're looking at that category, all you have to do is look at its nerve. Look at its nerve, right? Look at its nerve. That's a space, that's a topological space, which has all this mod P information about the group. You P completed, and it's homotopy equivalent to your original space, BG completed as P. So you took this combinatorial object, G, right? You did this horrible thing to it, took its classifying space and P completed it. Now you have a category, that has the same, so to speak, the same homotopy type, mod P, but it's a discrete object which contains only the P primary information, nothing else, okay? So, and it turns out this is very useful because, for instance, if you ask yourself, can I understand maps or self-maps of BG completed P? It turns out that the homotopy classes of equivalences, homotopy equivalences of BG completed are given by certain nice functors, like equivalences of categories of this category. Okay. Computing homotopy equivalences of maps in general of a space as complicated as this is impossible by standard technology of algebraic topology. To compute self-equivalences of a finite category, it's relatively easy. It's basically like looking at homomorphisms between groups. So we can only, unfortunately, do equivalences, but for a very good reason, but we can do something. So we could actually do some computations which were completely impossible before. Okay, well, that's very nice. But that's ancient history. It turns out, once you have that, you say, oh, that's interesting, because it was known for quite a while that there are some exotic examples, okay? In other words, these fusion systems, linking systems, they come from groups. But there's, from the 70s, there were examples of fusion patterns, or fusion systems if you want, that do not come from groups. Part of the classification theorem of finite simple groups involved a proof that there is a two-fusion system, which is completely consistent, so it satisfies whatever properties you need, but there's no group that contains it. Okay, this is called exotic. And so we were asking the question, well, can we do these things without assuming we have a group in the background, except for the CELO, for the P group? And it turns out that by work of Puch from the early 90s, Louis Puch defined abstract fusion systems. Okay, abstract fusion systems. What are these? Well, you have a group, a P group S. It's a category whose objects are the subgroups of S, just like in the case of a group. And then the morphisms are homomorphisms. They are required to be injections, so one-to-one homomorphisms, including all the ones which are induced by conjugation in S. But there is some more requirements which make the fusion system what he calls saturated. Okay, whatever that means. It's a bit technical. I'm not going to get into this. All right. If you have a saturated fusion system, then his hope was that this is going to give a way of thinking about things like the classification theorem of finite simple groups in abstract terms without going case by case by case by case and 10,000 pages of a theorem which no group theorist really believes fully, except for possibly the people who proved it. He never actually got to do that, right? But we picked up his idea and we said, okay, well, you have an abstract fusion system. Can you do an abstract linking system? So we formulated some requirements. We wrote a very nice paper about it, and we were able to prove all sorts of, coin some concepts and prove some nice theorems. And in particular, the thing that Bob Oliver by himself showed actually, that the Martino-Pridi statement going the other way, so Martino-Pridi claimed that if you have a homotopy equivalence of classifying spaces, then you have isomorphic fusion systems, but they failed in showing the other direction. What he showed is basically if you have an isomorphism of fusion systems, then you also have an isomorphism of linking systems, thus proving that the classifying spaces are the same. So that was one of the achievements of that theory. Beyond that, we coined the concept of what we call a P-local finite and then later on compact group, which basically is a triple with a CELO subgroup, a CELO group, which is some finite P group. In the finite case, fusion system associated to it, a la Puch, and then a linking system. And again, later, this was much later, when the theory was established, we did not know that every fusion system has an associated linking system, and we definitely did not know that it's unique, right? But later on, actually not so long ago, we were able to prove, in various combination of authors, that every fusion system, abstract or not, has an associated strategic linking system, therefore a classifying space of the fusion, okay? That gives you like a purely P-local homotopy theory of classifying spaces that doesn't actually depend on whether or not you're classifying a group, taking the classifying space of a group, but only the P-fusion pattern, okay? So that's the background for this talk. Now, so is that any questions at this point about the setup? All right. So like I said, once we had the finite concept established, then we decided to become a little greedier and think about the compact context. So Dwyer-Wilkerson defined back in the 90s, they defined P-compact groups, for instance, which was kind of homotopy theoretic P-local analog of the classifying spaces of compact Lie groups, okay? And they were able to prove lots of theorems which were similar, very similar to theorems that people proved about the homotopy theory of classifying spaces of compact Lie groups, but in a completely purely homotopy theoretic context, without ever referring to the group structure or to the smooth structure or anything of the sort, like the Lie algebra, nothing. So some known theorems were basically shown to be purely homotopy theoretic and don't need the structure, the actual structure of the compact Lie group. So that was very interesting. And so we thought, well, we might as well, since we have the finite concept, we might as well try to do the some compact analog. And so it turns out not to be very difficult. Well, in retrospect, the paper was written in 2000, well, it was published in 2007, which is almost 20 years ago. In retrospect, maybe not too difficult, but it was actually very difficult. So the idea is replace the group S by a discrete pictorial group. So what is discrete pictorial? Basically, S is discrete pictorial if it has a quotient which is a finite P group, and a kernel, it's an extension, by a discrete pictorius. Now, discrete pictorius is basically a group of the form ZP infinity to the n for some n, right? ZP infinity is the union of all the ZP to the R's with the natural inclusion. Okay. So it's, I mean, it sits canonically, for instance, inside a circle, okay? And it turns out, why is it called pictorial? Because it turns out if you take the classifying space of this group and you P-complete it, you're going to get the P-completion of CP infinity, okay? So actually, it is actually modeling a mod P, it's modeling S1, all right? Cool, so we have a replacement for the P group. We also, turns out that looking at the axioms that define a saturated fusion system over a finite P group, the same axioms make complete sense in the context of these discrete pictorial groups. And furthermore, well, there has to be a little bit of some small modifications. The only thing that requires an extra axiom is this, what we call the continuity axiom. In other words, if you have a sequence of morphisms between finite subgroups of that S, right? And it's an infinite sequence, you want the limit, the co-limit of that sequence to also be in your category as a morphism. So this is kind of a continuity axiom, okay? That's not guaranteed by the setup. But you add that and you have a system, okay? And again, later on, we were able to kind of establish the theory of P-local compact groups, able to prove all sorts of things about those things, like look at equivalences. We could very similar theorem to the one we have for finite groups. These are determined by equivalences of the linking system. And later on, kind of mimicking what was done for finite groups, Asaf Liebman and I were able to show that for every saturated fusion system over a discrete pictorial group, we have a unique classifying space, okay? A unique up to equivalence classifying space, so unique linking system up to isomorphism. All right. So that's all very nice. But there's a problem. You want to understand which ones of those objects come from groups or some known objects, and which are different, exotic in some sense. In the finite case, it's easy. So if S is finite and F is a fusion system, such that there does not exist any finite group G with FSG isomorphic to F, then we say F is exotic. Okay? And so there are examples of exotic fusion systems. I mean, the first one was established by Ron Salomon in 1974. It consists of, it took the fusion system of the group of Lie type spin 7 over FQ, right? Spin 7 over FQ has two conjugacy classes of involutions. It forced them to be conjugate to each other, okay? That fusion system is completely consistent but it's exotic. It does not come from any finite simple group or any other group for that matter. All right. So that's the first example. And then with Bob and Carlos, we found at odd primes, we found many other exotic examples that, objects like that will satisfy whatever you want from the homotopy theory point of view, but actually do not come from finite groups. What happens in the infinite case? In the infinite case, so for infinite S, what do we have? Compact Lie groups. Compact Lie groups, if you take the classifying space, take it to peak completion, it gives you a fusion system induced by the group itself, and a classifying space and a fusion system that is, what you want. So that works. That gives you a p-local compact group. A compact Lie group gives you the peak completion of the classifying space, gives you a classifying space of a p-local compact group, and the triple S F, the fusion system of the compact Lie group, and the associated linking system gives you an example. Great. What else? If you look at p-compact groups, these are these homotopy theoretic analogs by Dwyer-Wilkerson of compact Lie groups, right? Again, it's just a space. It's a space, which let's call it Bx for the sake of notation, Bx, such that the space itself is p-complete, okay? And if you take the loop space of Bx, call it X, that has finite mode p cohomology. That's the whole requirement. This is only obviously true for the classifying space of a compact Lie group. But if you just have that, you can build a whole homotopy theory and prove lots of theorems, which are basically almost the entire homotopy theory of compact Lie groups, purely homotopy theoretically. So compact Lie groups again give rise to p-local compact groups. Very nice. What else? Well, it turns out that if you're looking at what is called linear torsion groups, linear torsion groups. So what are these? These are groups G. There are subgroups, or let's call them gamma. Gamma, which are subgroups of some GLN of some ring R, such that, not a real number, just an arbitrary ring R, such that for every X in gamma, X to the K is 1 for some K. So a discrete group sitting in some linear group such that every element is finite order. Not necessarily any particular finite order, but finite order. These are linear torsion groups. These also, each and every one of those gives rise to a p-local compact group. So what on earth could be exotic? I mean, these are very, very well-defined classes. The compact Lie groups, the simple compact Lie groups are all classified. P-compact groups, 2 big papers in the early 2000s. The analog of the simple ones are classified. So we know them, okay? But this could be any ring, all right? So the question of exoticity goes out the window, at least so we thought at the time. We could not figure out whether there is anything that is not coming in one way or another from the group. And that's the realizability question that is in the title of my talk. So that's where the talk actually starts half an hour later. Okay. So after all this time, why did we think that we can actually make a difference? So this question was, out for a long time. What does it mean to be an exotic p-local compact group? And, what can we say, in any sort of generality about this question? What made a difference was a paper that was written by Alex Gonzalez, which showed the following. It showed that every p-local compact group is a co-limit of p-local finite groups. It's Gonzalez. Okay, and that was a major achievement because it sounds like, you know, almost like an obvious thing, but it really isn't. It's a very, very hard theorem published in Geometry and Topology. Well, the problem is to show, well, you have inspiration from the homotopy theory of compact Lie groups. So there's a theorem by Friedlander and Mislin that says something similar. So if you look at an algebraic group satisfying certain conditions over the complex numbers, you can take its classifying space and you can complete it at the prime P or Q, let's say Q, okay? You can take then that space 2 times. Can you see this? This okay? 2 times. You can then take the diagonal map on one end and the identity and on one factor and the unstable Adams operation psi q to the r, or not q, p to the r, sorry, right? And what you get here is the corresponding BG over p to the r, or fp to the r, completed at q. Okay, so q and p have to be different. So this is a theorem of Friedlander and Mislin. With some background from some particular case proven by Quillen when he defined the algebraic K theory of finite fields, of all the fields in general. Yeah. Sorry? Which one? This one? So that's on one factor is the identity, the other factor is the unstable Adams operation. Okay. So in particular, you know, the unstable Adams operations are natural, and if you increase the power indefinitely, eventually you're going to get this guy in here as well. Okay, everything here is P complete. Q complete, sorry. Okay, so in this case, you have all these maps are actually the maps, you know, if you just look at the Adams operations, it's not induced by a homomorphism. And so when you look at how these things included in each other, they are not included in each other as homomorphisms, but still you have that the co-limit is the classifying space of the extra compact Lie group. Okay, so that gave us the idea of defining a concept which we call sequentially realizable. So definition, a fusion system is called sequentially realizable. Realizable if, let's call it F. If F is the union of Fi, okay, so you have a sequence Fi plus 1, etc. A union of these Fi, I larger or equal than something, such that each Fi is the fusion system of some finite group. Okay, Each Fi is a fusion system of some finite group, but you don't require these finite groups to have any relationship with each other. Okay, so it's not like you have a sequence of homomorphisms, which will give you a sequence of fusion systems, right? But rather, you have a sequence of fusion systems that you can define, but all that it requires really is to have inclusions of the CELO groups, okay, and some compatibility. And then F is that union, all right, the sequentially realizable. Okay, well, I have to make one remark before I continue. As a matter of fact, any fusion system, saturated or not, so whether it satisfies all the requirements or only part of them, can be realized as a fusion system of some group. That's going to be a confusing statement. What do I mean by that? You can make an amalgam, right? You can use the structure of the fusion system to make an amalgam, right? That has a maximal finite P group or a maximal discrete pictorial group, subgroup, and the fusion patterns in the group between the different subgroups of that maximal P subgroup will give you the original fusion system. You can always do that. So the question of whether you can realize the fusion system by a discrete group, it has a very simple answer. But that amalgam, right, for instance, will have a completely wrong classifying space. It has a lot of other structure which has nothing to do with the original fusion system or the homotopy theory. If you are interested in the homotopy theory or the representation theory of your group, of your fusion system, then this doesn't do the job. Okay, that's been known for a while. So what we were after really is to do something, to look at something like this, where everything is realizable at every finite stage, but when you go to the end, maybe it isn't. Okay. All right. So the first question is, suppose you have a finite fusion system. Is it sequentially realizable? So the first theorem we proved in this subject, these are two papers that are currently being reviewed. The first theorem that we proved and gave us some hope that we can answer the question is the following. Suppose, I'm not sure why a theorem like that should give anybody any hope, but you'll see what I mean. So suppose F is a fusion system over a finite P group. That is sequentially realizable. Okay? We know that there are exotic, so you see, again, over a finite P group, you know what it means to be exotic. Exotic means it's not realizable by a finite P group, by a finite group. Okay? Suppose it is, however, sequentially realizable. Maybe it's a sequence of groups, maybe infinite groups, because that can happen, like I just told you. Infinite groups that do realize that fusion system. Okay? So if it's sequentially realizable, then it is finitely realizable. In other words, for finite fusion systems, sequential realizability gives you nothing new. If it's sequentially realizable, it remains, if it's exotic, just not coming from a finite, finite group, then the sequential realizability will not do the trick. Okay, this was one partly encouraging because we can use the methods to say something, and partly discouraging because you don't get anything new. Then we have another observation. Sequential realizability is actually an amazing, it looks like a very powerful kind of concept. But it turns out that you could have fusion systems which are at the same time sequentially realizable, but also the co-limit of a sequence of exotic. So you can have a sequence where you have, say, for every even index, you have the fusion system of a finite group, and for every odd index, it's exotic. Okay? So sequentially exotic does not make sense. So now that we know that sequentially realizable is a concept that has to be handled with care, right? We can try to ask the question of what is and isn't sequentially realizable. Make sense? Yeah? No, because you can have an example where you have a sequence of fusion systems, including in each other, just like are defined, where say every even one will be one of a finite group, and every odd one will be exotic. You can have all exotic. Take the subsequence of all odd ones. Yeah. But it's not sequentially exotic because it's also sequentially realizable. So at the same time, it's both exotic and realizable. So you don't want to define sequentially exotic. Okay? Okay. All right. So where am I? Right. So let's look at some examples. So in particular, so examples. The first example is, of course, I already talked about it. It's the linear torsion groups. Okay, linear torsion groups. So what can we say about those? So, examples, for instance, something like of the form GLN F Q bar, okay? Any subgroup of that, okay? So, so these are all sequentially realizable. How do you do it? Well, you show that any linear torsion group you can actually look, it can be considered as a subgroup of one of those. And then you just look at the intersection with the finite subgroups. The finite, if you look at the FQ to the K, you intersect with those, and then you get a sequence of groups which gives you a sequential realizability. Okay? Then another example. So that's a theorem. So if P is a prime and G is a compact Lie group, and G is a compact Lie group, where then its fusion system is sequentially realizable. Now, here I have to make a comment. So for a a connected compact Lie group, that's an easy theorem. It's easy once you know Friedlander and Mislin, because they show that you have this square there, and they show basically that every classifying space of a compact Lie group, but some mild conditions, is in fact a co-limit of these finite things, and therefore you have something better than just sequentially realizable. You have linear torsion realizable. So it's a weaker property. Okay, so for connected compact Lie groups, it's easy. It becomes more complicated, and in fact, significantly more complicated, if the compact Lie group is not connected. When it has a group of components, then the classifying space has a pi1, and you have to work a little harder. So, but the theorem here actually includes, basically what you do is you look at the defining extension. So this is a one-line proof. The proof is more than one line, I'm afraid, but this is a one-line proof. So for connected, it follows from Friedlander-Mislin. For non-connected, you consider the group of components. Sorry, not the group of components, the connected component. Look at this extension, right? Take its classifying space. There's a vibration. And then you have to find, basically, you know what to do with this guy. This guy is sequentially realizable, and you have to lift that realization to BG. Okay, it involves a little bit of fiddling. It's quite an involved theorem, but it's possible to do. We eventually found a way to do it in two ways, so it's good. Okay, so compact Lie groups are all sequentially realizable. Okay, so compact Lie groups, you cannot consider their fusion systems exotic, because after all, what's more natural, non-exotic than a compact Lie group? What about p-compact groups? P-compact groups, well, if you take the classifying space of a compact Lie group and you p-complete it, you get the classifying space of a p-compact group. So these are the non-exotic, but there are exotic, there exist exotic p-compact groups. Okay, they exist. Ones that do not come from a compact Lie group. For instance, the most famous one is the one called BDI4. DI stands for Dixon invariance. So that's it's a p-compact group at prime 2, whose cohomology is the mod 2 Dixon invariance of rank 4. Okay, so it's a polynomial algebra on classes on degrees 8, 12, 14, and 15. Okay, with synod operations connecting them. They exist for the prime 2. They exist for 1, 2, 3, 4. 5 is already not only exotic, but doesn't actually exist. And there's a famous story about it, that where there was one proof that's of non-existence, another one of existence. The non-existence won. Anyway, here's an exotic one. This does not come from a compact Lie group. Okay, so what about those? And there exist more of them. At odd primes, there exist more of them. At the prime 2, there's the only one. Okay. Right. So another theorem is, it's going to be a funny theorem. And I'm going to give you the full extent of it, because that involves, for that I wouldn't have to use slides. So among the exotic p-compact groups, some are sequentially realizable, and some are not. That's not a very good theorem, is it? But the actual theorem is there is a complete classification. We know among all the simple, like I told you before, the simple p-compact groups are all classified. We know the whole list of them. So, and we know exactly which ones are and which ones are not. Okay, some of them are, surprisingly enough, sequentially realizable. You can realize them by a sequence of fusion systems, all of which are realizable over finite groups. Okay, similar to what Gonzalez did. Okay, and some of them are not realizable. For instance, this guy remains exotic. Okay, cannot be realized even by a sequence of finite things. It's not very surprising because if you look at this guy here, it also admits this unstable Adams operations. And if you look at the corresponding pullback square, right, you get classifying spaces that Dave Benson called the classifying space of a finite simple group that does not exist because the fusion system is exotic. Okay. And so this is a colimit of those exotic things, exotic finite things, right? But so the contents of this theorem for that BDI4 is that you cannot do it any other way, basically. There's no finite thing that will approximate it. Okay. All right. So, okay. What else can I say? I have about 10 minutes. Great. So, we'll make a definition. So G is P-Artinian. P-Artinian if every P subgroup P in G is Artinian. Artinian means the descending chain condition is satisfied. And of course, I'm talking here, when I say a P subgroup, I include discrete pictorial, okay? Or I include all possible groups such that every element is a P power order. So in particular, if you take an infinite countable product of ZPs, yeah, every element is order P, every non-trivial element is order P, but it's not P-Artinian because you can have a sequence of subgroups which is not finite, which doesn't stabilize. Okay. So that's P-Artinian and strongly P-Artinian. P-Artinian. If every sequence of finite abelian P1, P2, etc., finite abelian P groups, P subgroups, satisfies the centralizers. So centralizer of P1 includes the centralizer of P2, stabilizes. Okay. So there is a reason which I'm not going to get, technical reason which I'm not going to get into of why we bother to define these things, but now we're going to make two more definitions. So we said that a fusion system F is LFS realizable. If there exists a locally finite group, locally finite strongly P-Artinian, gamma, such that F is F S of gamma is isomorphic to F, where for some S in the CeLO P subgroups of gamma. Now, the point is that when a group is strongly P-Artinian, it has a CeLO P subgroup. It has a maximal P subgroup such that all the rest of them are conjugate to it. Okay? All right. So that's LFS realizable. Not possible with one hand. All right. Okay. Now, if you remove the strongly P-Artinian condition, you can just look at locally finite. By the way, I didn't say it, so I should maybe mention it. Locally finite means that every finitely generated subgroup is actually finite. Okay. Right. So. Right. So. So if you have F is LF realizable, so LF locally finite realizable, if there exists a locally finite Peartinian gamma such that, and now I have to be a little careful because now the existence of a CELO is not guaranteed. But what you can say is that there is a maximal, there exists a maximal P subgroup so that every finite P subgroup is conjugate to it. Sorry, no, every finite P subgroup is isomorphic to a subgroup of it. So in particular, all of these maximals are the same, but not necessarily through conjugations. It's a weaker statement, okay? Such that F is isomorphic to a closure of F S gamma, whatever closure means. I mean, basically, I will have problems because of that condition that it doesn't hold, the centralizers. I'll have problem with the continuity axiom for P-local compact groups, okay? So I need the closure of this. But then I say it's LF realizable if there exists such a locally finite Peartinian group such that the closure is isomorphic to F, all right? And it turns out that these concepts are nested nicely. So if you're looking at sequentially realizable, that's the strongest, okay? Sequentially realizable is the strongest. Then you have LF realizable. And then you have LF with CELO realizable. And then you have linear torsion realizable. And there is an implication like that. So this is the strongest feature that we are aware of anyway, right? And all of these things are included in each other. It's easy to show that there are examples that are distinguishable families. What is difficult to show is that there's any example that is realizable by one of them and not by all of them. So we don't really know that they are different. Although the concepts are different, the realizability properties are not. We might be able to show at some point that sequentially realizable if and only if linear torsion realizable. We don't know that yet. Okay? I'm going to use another minute to say what we to tell you what we can say further with this. So for instance, we were able to show, so in finite group cohomology, there is a very famous theorem by, a very useful theorem by Cartan-Eilenberg, which is called the stable elements theorem. The stable elements theorem says that if you know the cohomology of the CELO P subgroup, and you know the cohomology of the subgroups of the CELO P subgroup, and how they are related, how the cohomologies are related through conjugation homomorphisms, okay? Then the subgroup of the cohomology of S, which consists of the elements stable under all these conjugations, is the actual cohomology of G modulo P. Okay, it's called the stable elements theorem. Another way of saying it, look at the fusion system, look at the cohomology as a functor from the fusion system into rings, if you wish, algebras, and then take the limit. The limit is the cohomology of the group. Limit over the fusion system, the cohomology of the subgroups is the cohomology of the group mod P, all right? So it turns out, part of the work that we've done here, it turns out that this is really a lot stronger. So here's a theorem I actually like very much. So if G is locally finite, G is locally finite, S is a P subgroup. Such that the only requirement, every finite, so I don't want it to be Peartinian or anything of those fancy properties from before. Every finite subgroup, every finite P in G is subconjugate to S. To S. Then H star of G mod P to H star of S mod P is injective. Injective, and the image is the sub-algebra of stable elements. So that's a theorem. One of the consequences of Gonzalez's theorem is that this holds for p-local compact groups. The stable elements theorem holds for p-local compact groups. Actually, it's a lot more general than that. Well, at least if you talk about the ones which are realizable by those locally finite groups. So it's that's another consequence of the work. And I'll stop here. Thank you.
Okay, thanks. Questions? Berran, how do you abstract the realizability in the various cases?
Sorry?
You need some abstraction to say something is not realizable, sequentially realizable. Which kind of abstraction you use?
So to be sequentially realizable, you have to have a sequence of subgroups. It's not abstractions really, is it? Huh? Well, like I said, I cannot say something is exotic. I just say that it's not realizable by a sequence of finite things. Oh, I see. So, well, most cases is by looking at the classification. So first of all, you reduce the question, you have a fusion system, you reduce the question to, you look at the finite quotient. Sorry, simple quotient. So you reduce the classification of finite simple groups, look at the fusion patterns there, it doesn't fit, doesn't work. There are more clever examples of cases where you can actually do this free of the classification. I cannot do this. Most people I know cannot do this. Some group theorists like Ron Solomon can do it. There is actually the statement that every fusion system has an associated linking system, so classifying space. The original proofs require the classification theorem, both in the finite and the compact case. But more recently, Justin Lind and I forgot the name of the other one. He's a very senior dude. I forgot his name. They produce a classification-free proof of that. But most of the statements that I'm aware of were done basically by reducing to the simple case and then looking at the fusion patterns there.
Other question? I have another question. So you were talking about sequential realizability, and this is basically, I can see maybe a sequence of fusion systems, like maybe the index is a linear poset. Can you think about the realizability via other diagrams?
Yes.
Is it related to those as well, or
no? So what you can do basically, in fact, this subject is very closely related to the question: can you express a classifying space as a colimit over some category where the ingredients are simpler than the one you're trying to approximate? Okay, so there are some very beautiful theorems from, well, with roots all the way to Quillen in the 70s that tell you, the famous F-isomorphism theorem, which tell you that over the fusion system or the orbit category, you can take functors where the values are classifying spaces of P subgroups or other subgroups. And then the colimit gives you a map to BG and a homology isomorphism. That's very closely related. So it turns out that you can actually construct, for every p-local compact group, you can construct such things, such colimits, okay? The question whether the ingredients come necessarily from realizable things, well, it does. It does, right? Because you're looking at basically the things like the automorphism groups of within the category of a particular object. And then when you take the co-limit, you get it. But that's cheating because you're using a lot of information. So that's a lot more straightforward, the sequential realizability.
No further question. Let's asynchronize again.
Now we have Shuchita Goyal from the Birla Institute of Technology and Science, Pilani, which will talk about Bousfield localization of posets.
Am I audible? Okay. So good afternoon, everyone. I would like to thank organizers for giving me this opportunity to speak here. And as we all know, we have Leaning Tower of Pisa here, which is one of the, I mean, not here in the talk, in the city. Yeah, right across, which is one of the 7 wonders of the world. And in India, there is another wonder, which is called Taj Mahal. And coincidentally or not, I actually belong to the city of Taj. So apart from Taj Mahal, Leaning Tower of Pisa, Colosseum are the new additions to the list of wonders which I have seen. So thank you for the personal reasons as well. And coming back to the business, so I'll be talking about the Bousfield localizations on posets. This is a joint work with Andres and others, which we started last year during NMRC. So let's go through the outline. I will have very little definitions, like literally least possible, in particular 3. I'll have transfer systems, then I'll move to model category structure and Bousfield localizations. Everything else will be built from here. So after this, once we have the base ready, we'll see the motivation, why this particular talk is here, why I want to talk about what I want to, and see its generalization to higher dimensions. So as I promised, first definition, transfer systems. These are nothing but in a category, if you take a sub-wide category, which is closed under pullbacks by arbitrary morphisms of the category, then this subcategory is called a transfer system on that category. And for this particular talk, I would be restricting myself to a very specific case because I want to work with lattices and they can be arrived at through this structure. So if I take any abelian group, I will define sub G as my category where objects are these conjugacy classes of subgroups of the graph, whereas the morphism exists from a subgroup H to a subgroup K if and only if H is a subgroup of K. So as many of you might have already predicted, if I want to generate a lattice out of this sort of a structure, I am going to look at groups which have subgroups in a very nice enough fashion. And so, okay, even before that, transfer system in this particular context gives me a partial order on this sub G, which is going to refine the inclusion, and it is closed under conjugation and restriction. So if I would take this particular group CPQ, where P and Q are primes, I precisely know all the subgroups. It's either the trivial group or CP or CQ, right? So the particular lattice which corresponds to this sub of CPQ will look like a square grid, right? So I will, let's say, have my E here. I will have my CP here, CQ here, and CPQ here. So as we saw here, this is coming through this subgroup. So E is a subgroup of CP, E is also a subgroup of CQ, CQ is a subgroup of CPQ, and CP is a subgroup of CPQ. So there is a direction in which these morphisms are exist, I will not have directions like this or this, and of course I have this. So these are my morphisms which are there for this sub of CPQ. So exactly this notation which I have told here. So the point in the 0, 0th location, which is this, is my identity group. And then on the 1, 0, I'll have CP. On 0, 1, I'll have CQ. And on the 1, 1, I will have CPQ. So this is it. Once this is clear, rest of the things should follow. So all the possible transfer systems that I will have. So, okay, if I have to reread this thing without looking at these items, I would shorthand this through just this. Correct? Because I'm going to suppress all of these notations. Because now I know which dot represents what. And with all of that, this is nothing but, it's a total order here, it's a total order here, and what you have taken is a product of these two total orders, which is your 1 cross 1. So apologies for people who take 1 as literally 1 and not 0, 1. Me being in between computer science and the topology, I'll take it with 0. So these are all the transfer systems on my 1 cross 1 grid. And there are exactly 10 of these. So coming to the next definition, a model category structure. This is a structure which I have on a category having 3 distinguished classes of morphisms. First being weak equivalences, vibrations, and cofibrations. Each of these I would demand to be closed under compositions, and they have to satisfy a set of axioms, which we will now see. So first one is that the category C itself should have all the finite limits and colimits. The class of weak equivalences W should satisfy the 2 out of 3 property, which just means that whenever I have composable maps between the 3 objects like this, and I have this, so there are 3 maps in the question. Whenever any 2 of these are in W, that forces the third one also to be in W. That is my 2 out of 3 property, not my. The 3 distinguished classes, each of these should be closed undertaking retracts in the arrow category, which means you should have a retraction, another retraction, and then the in-between thing being retraction implies the outer ones being retractions. So MC4, which we also say as the lifting property, which is that whenever I will have a commutative diagram of this form, so here this map I and P are special in the sense that whenever this is in the intersection of W and C, which we will call as acyclic cofibrations. These were cofibrations, remember, and these are weak equivalences. So the maps which are both are acyclic cofibrations for me. Whenever I have this coming from acyclic cofibrations, I'll also term that as AC, and P being a fibration, I should have a lift here. Also, whenever this is a cofibration and this is an acyclic fibration. So dually, we do understand already what acyclic fibration should be. These are nothing but maps which are both weak equivalences as well as fibrations. So when that happens, then also I should have a lift. In both of these situations, I am expecting a lift. If that happens, that is my MC4, the lifting property, or rather axiom. Last one for the model structure is the factorization axiom, which says that if you take any morphism of the category, one should be able to factor it as a cofibration followed by an acyclic fibration, as well as an acyclic cofibration followed by a fibration. It is not like if this holds, this one can let go of. We would want both of these factorizations to be possible. And that's when we say the factorization axiom is satisfied. So these are my 5 axioms which the model structure is required to satisfy for these 3 distinguished classes of morphisms. And good news is any of these tuples, so in this particular slide and the previous one, we have seen there are symbols like W, C, F, AC, AF. Okay. Thing is, if I consider any of this tuple, just the things which are mentioned there are enough to give you all others. So for instance, if I take this itself seems like a lot. In fact, it's a superset of this. So let me work with this one. So if let's say I consider W, comma F. So if I take the intersection, I'll have AF, the acyclic fibrations. And then this lifting property is going to give me the cofibrations, which are exactly the maps which lift on the left of the acyclic fibrations. And once I have cofibrations, I will come back to this, take its intersection, and I will have acyclic cofibrations as well. And similarly, the others could be done. This looks a bit new. So if I, let's say, have AF and AC, W can be obtained by taking the composition. AFs followed by ACs followed by AFs gives you W. And then AF gives me C by the lifting property. AC gives me F by the lifting properties. So all of that is in place. Good. Oops. Why do I care about all of this? There has to be some relation. And the relation is that if I take a lattice which has a model structure, then the acyclic fibrations on this lattice forms a transfer system. And this is why I would want to see transfer systems / model structures on lattices, studying the other object, and doing vice versa back and forth. So Bousfield localizations, it's a formal way of increasing your set of weak equivalences, if I may even call it a set. And what do? We literally start with a model structure. If it's a model structure, it has to have a class of weak equivalences. You want to increase this particular class, but at the same time, you either keep your cofibrations fixed or your fibrations fixed. And that tells me that there are going to be 2 sorts of localizations, left or the right. In both the cases, this has to increase as part of the definition. In the left one, I take cofibrations unchanged, which by the lifting property tells me that acyclic fibrations remains unchanged. And if I come to the right Bousfield localizations, I will keep my fibrations class fixed, which also keeps the class of acyclic cofibrations fixed. And the motivation why all this should be done or should be asked is Balchin and others in 2023, a paper came out which says transfer systems on finite total orders, where they looked at the model structures on this particular object. And the aim to begin with, they were looking at the transfer systems / model structures through a search on the integer sequence encyclopedia. It turns out that they're same. And that's when all this theory was constructed, that they indeed are the same. So the result, which is there, I mean, this was another part of the motivation why people care about model structures in the context of transfer systems and vice versa. But what they proved in this particular paper is that any model structure on this total finite order can be obtained starting from the trivial model structure. So trivial model structure is what? Where weak equivalences are just the identity morphisms and nothing else is there, via a sequence of left and right Bousfield localizations. So then a very standard canonical question which would come to our mind is, what happens if I take product of these total orders? What happens? And that's exactly the question we started asking and started working on in the last summers. So remember, we looked at the 1x1, all the transfer systems. Now here, this is my center. And as you can see, let me just go a bit. So these red boxes which you see, so this one block is one thing, like one transfer system / model structure. And then these smaller red blocks are actually giving me the class of weak equivalences. So if this is disjoint from this, which means this and this, there is no weak equivalence in between them. And similarly for the others. So this is my trivial model structure. Now from here, if I take its right Bousfield localization along this particular arrow, then I get here. If I take its left Bousfield localization along this arrow, the same arrow, I get here. And like this, you can read the entire chart. So there are a total of 23 model structures on 1x1. All of these are listed here, which also means that all of the model structures on 1x1 can be arrived at through a sequence of left and right Bousfield localizations, which is a good news. We were expecting exactly this. And what happens if I increase any of the directions? So if, let's say, I go for m cross n for any higher value, boom, this does not hold true. And the counterexample exists in 2x1 itself. You don't even have to go much far. Counterexample is here. So this is a valid model structure, but it does not come through left or right Bousfield localization of any other model structure on the 2x1 grid. So that's what I've written. And let's see a quick proof. So at least for the left Bousfield localization, it is more straightforward. So I can give the full proof. So suppose it is about left Bousfield localization. So I have shorthanded, taking inspiration from the almost prescribed linear thing from yesterday's talk. So suppose it is a left Bousfield localization of a model structure, of some other model structure on the 2x1, what would have happened? Coming back to the definition, left Bousfield localization keeps C unchanged and hence AF unchanged. So we will just remember this bit. So if the acyclic fibrations have to remain unchanged, okay, that made me realize one mistake which I have done. So the arrows which we see here are my acyclic fibrations. Co-fibrations information I have completely hidden from here. We can figure them out from this data itself. And this is why the data that I'm showing here on this board is just the weak equivalence classes and the acyclic fibrations. So all the morphisms, as you can see, they have two heads. So these are acyclic fibrations, the standard notation. All right, so this left Bousfield localizations preserves my acyclic fibrations, which means before localizing itself, the model structure has to have the same set of acyclic fibrations, but fewer weak equivalences. Because you're doing a localization, so of course you're increasing some weak equivalences. If this is my, this is the same example which was there on the previous slide, trust me on that. For this one, all of these maps are my acyclic fibrations. Oh, there's a typo. I have this curved arrow also. So this is there. All of these are acyclic fibrations. They should remain present in the model structure before localization itself, correct? But the class of weak equivalences should have been strictly lesser. However, if we look at this particular long diagonal, from 0, 1 to 2, 1, it should have been in an acyclic fibration. In particular, it should have been a weak equivalence, which means this also should have been a weak equivalence. So there is no place where you could have shortened your point, shortened the class of weak equivalences. You see, as a graph, if I want to see this, it is a connected graph, which means all of these elements are weakly equivalent to each other. Two out of three property, all of that is in place. So this has to be in W, but then we are saying W should have been a smaller subset, which is a contradiction. So it could not have been a left Bousfield localization. Let's see what happens if I look at the right Bousfield localizations. If at all it is a right Bousfield localization of any other model structure on 2 cross 1, what would have been my acyclic cofibrations? Exactly the complement set of acyclic fibrations. And hence, so not to sound bossy, but if you just remember this for a sec, and I will flash this again. So here, if we see, this is the map which is missing, this is the map which is missing, and then this curved map is missing. And then that's what I get. So these are the maps which are there in the acyclic cofibration set. And now, since acyclic cofibrations are preserved, I know that each of these maps should have existed as an acyclic cofibration in the previous model structure itself, from where I would have tried right localizing. But I would want fewer W's in my previous model structure. And if we see this, the only disconnection which is possible is at this point, right? So exactly that is what we are going to do. This implies this for the choice of W. And once I have this as my W, possibilities of including new weak equivalences in the hope of localizing it is through this or this or this or this or this. But as people are already observing, thank you. So 2 out of 3 is ensuring that if I take care of this or this map, that is going to give me the rest. If I could say that, it is a problem if I try to add this map to the set of weak equivalences or this map to the set of weak equivalences, again, I'm already in problem. So right localization of this model structure along this arrow or this arrow will not give me this arrow as the acyclic fibration, and that requires a bit of explanation. So I'll again keep it under the carpet. However, this does tell me that the structure which I started with is not a left or a right Bousfield localization of any other model structure on 2 cross 1, which brings me to this result. There are many more results in this paper, which again I'm keeping under the carpet because the paper is in preprint stage as of now. So yes, let me also go through the references quickly. So this is the paper from where this motivation came about the total orders, model structures on finite total orders. This is where Balchin, Kyle, and Kalika and Constanze looked at all the model structures on the total order n. And just to actually make a point, so this is, oops. This is not the only problematic thing in the 2 cross 1. There are actually 16 such structures which do not appear as a left or right Bousfield localization of any other model structure, even though there are a total of 182 transfer systems, model structures on this particular grid. So, yes. And this is the one which soon should be out on archive at least. Thank you.
Are there any questions? I have one. Do you know on higher lattices how these non-left or right Bousfield localization behave? How many there are?
Sorry, can you please?
Okay. You found out that in the grid 2 by 1,
Yeah.
there are a number of non-Bousfield localizations. Can you say something about the number in higher grids?
That we do not have as yet. This one is also exhaustive in the sense that when we look at the model structures, then within model structures, there is a concept of saturated and unsaturated. And seems like once you have hit an unsaturated model structure, whether you do a left localization or a right localization, you're going to be away from that trivial one.
Yes.
So saturated ones, once you have the...
So you kind of have a condition which says is not a left.
It's not always there. So what I'm saying is, if let's say I start with an unsaturated model structure on an M cross N grid, and I do a left localization or a right localization, the resultant model structure will also be unsaturated. And what it looks like is that unsaturated are the ones which have the difficulty of not being able to achieve through a sequence of left and right, starting from the trivial one.
Okay, but you don't know the number.
There is no...
as of
yeah,
yet.
yeah, yeah.
As of yet. Thank you.
So actually, even for the M cross N, how many model structures are there in total? That also is computed through computer. There is there is an algorithm which Scott Balchin has developed. And I mean, it takes huge time.
There is no closed formula for that.
There is no closed form formula.
Thank you.
Yeah, it goes into millions as soon as you just touch 4 and 5.
Okay.
So it runs exponentially. Yeah.
I see. If we have no other questions, let's thank Shuchita again.